Hello, welcome to the course of Excelling with Mathematical Modeling. Today we will be discussing about the stability of a system. We will start with the equilibrium solution and then we will move up to the stability of the system. What do you mean by an equilibrium solution or a steady state solution? So, if we consider a system of n nonlinear autonomous differential equation, by autonomous, we mean that your differential equation dx dt, this side will not contain explicitly the function of time. That means it will be dx dt equal to some function of x, but I cannot put any function of time here. So, that is it is an autonomous system. So, we consider an autonomous system and we define that the steady state solution or equilibrium solution or critical point, there is another name fixed point. By all this we mean that the solution of the system when the value of this x does not change with time. And what does that mean? If your x does not change with time, obviously your dx dt will be equal to 0, which is equal to f x star. So, we put the right hand side equal to 0 and we calculate our steady state solution or equilibrium solution or critical point or fixed point. So, if you have dx dt equal to some function of x, because it is an autonomous system, to find the steady state solution, all you have to do is put this equal to 0 and calculate that value of x for which this equation gives a 0 solution. If that value of x is x star, which we called a steady state solution or fixed point or equilibrium point, then at this point f of x star must be equal to 0. And this happens because from the definition where there is no change in the solution as you vary x. Let us take an example. So, if you want to find the steady state solution of dx dt equal to x square minus 9. So, as told before, all you have to do is the steady state solution is obtained when your dx dt is equal to 0, which will imply x square minus 9 is equal to 0, which implies x square equal to 9 and which implies x equal to plus minus 3. So, x equal to minus 3 and x equal to plus 3 is your steady state solution or fixed point or critical point. We move to our second example. You have to find the equilibrium solution of dx dt equal to minus x cube plus 3x square minus 2x. As we previously done, we take dx dt equal to 0, which will imply minus x cube plus 3x square minus 2x equal to 0, which will imply I take x common. So, minus x square plus 3x minus 2 equal to 0, and if you factorize them, it is x minus 1 into x minus 2 with a negative sign which you can take to the right hand side becomes 0. So, you have your equilibrium solutions to be 0, 1 and 2. So, I guess it is very much clear when we have a single equation and you have to find the steady state solution or equilibrium solution, you put dx dt equal to 0 and whatever the expression in the right hand side, you take that equal to 0, solve the equation and whatever roots you get, those are the equilibrium solutions or steady state solution or fixed points. Let us take an example where there are no numericals, but we have the parameters like r, k, e, these are the parameters here. So, to obtain the critical point of this particular equation, it is the same. We now put dx dt equal to 0, which will imply R x 1 minus x by k minus E x equal to 0. So, 1 x will come out and you are left with R into 1 minus x by k minus E equal to 0. One of the solution is x equal to 0, and to solve the other one you just take R 1 minus x by k minus E equal to 0, which will imply 1 minus x by k equal to E by R, which implies x by k equal to 1 minus E by R. This implies your x is equal to k times 1 minus E by R. Now, if we simplify, this is k times R minus E by R. Sometimes in the book you will see that the notation is x star, because we denote the equilibrium solutions with x star. Actually, it is the value of x for which you are getting the equilibrium solution, and the notation is x star. Now, if your equation, this equation, right now it is just a differential equation, but when you will be doing the modeling, this will have some specific meaning. This may represent a population. So, if it represents a population, then we have always the positive values. So, either it is a 0 value or we have positive value, we cannot have a negative value. In that case, you have to take care of this equilibrium solution, that so that this becomes positive. If such is the case, where your differential equation represents some cells or some population, in that case your equilibrium solution has to be positive, and for that you must have k times R minus E by R must be greater than 0, and which will imply that your R minus E is greater than 0 and R is greater than E. So, this is the condition which you have to mention such that your critical point or your equilibrium solution is positive. And this happens only when you know that your model will give you a positive solution only, and it cannot give a negative solution. Let us now take two equations. So, if you want to find the equilibrium solution of two equations, so let me put in the form x star and y star. So, if x star y star is the equilibrium solution, and to find them you have to put dx dt equal to 0 and dy dt equal to 0. Now, if dx dt is equal to 0, obviously you get x minus y equal to 0 and 1 minus xy square equal to 0. This implies x is equal to y, and this implies xy square equal to 1. And since x is equal to y or y is equal to x, you substitute it here. Say I put y equal to x, and this will imply x into x square equal to 1, which gives x cube equal to 1. So, one of the solution is x equal to 1, which you can already see. Otherwise, you take it to the right hand side, put them equal to 0, factorize them, and this will give you x equal to 1. And if you put this equal to 0 and try to find the solution, x square plus x plus 1 equal to 0, we use x equal to minus b plus minus root over b square minus 4ac divided by 2a, and you can see there is a negative minus 3 inside the square root. So, this will give you an imaginary solution, and hence x equal to 1 is the only real solution here. And since x equal to 1 and x is equal to y, we have y is also equal to 1. So, 1 1 is your steady state solution here, or equilibrium solution. We take another example where we have, instead of numericals, we have put x and y, the parameters a, b, c and d. As defined before, our equilibrium solution will be dx dt equal to 0, which will give us ax minus bxy equal to 0, which gives us, take x common, a minus by equal to 0, which gives x equal to 0 and y equal to a by b. In the similar manner, we put dy dt equal to 0, which gives minus cy plus dxy equal to 0. Can take y common, minus c plus dx equal to 0, which implies y equal to 0 and x equal to c by d. Now, how to choose the combinations here? Let me explain it in two ways. The very first is, here x equal to 0. So, you put it in the second equation like this one and see what you get. So, if I put x equal to 0 here, I get minus cy plus 0 equal to 0, which implies y equal to 0. So, I have, when x is equal to 0, from this I got from the first equation, I put it in the second equation and I calculate the value of y, which is y equal to 0. So, clearly 0 0 is one of the fixed point or steady state solution or equilibrium solution. Now, you put y equal to a by b. So, if you put y equal to a by b, you can see here the computation is x is equal to c by d. So, what another solution is c by d comma a by b. Well, how do you get that? See, if you put it here, y equal to, so I have the equation minus c plus dx equal to 0. So, if I put y equal to a by b here, I get minus c plus dx equal to 0. This is not 0, so only thing is this is equal to 0, which gives me x equal to c by d. So, x star y star is c by d and a by b. Now, there is another way to check. There is a common mistake that people take it as a combination like x0, y0, x0, then c by d, y a by b. So, all four combinations they try to take. So, you have 0 0, you have x star 0, you have 0 y star and you have x star y star. These are all possible computations of the equilibrium solution that you may get. So, another way to check is that you just put this value here and see whether it is satisfying or not. So, if I put this value here 0 0, this satisfies, 0 0, this satisfies. So, clearly this is a steady state solution. Now, I put x star 0. So, if I put x star 0 here, what I will get? A x star minus b x star into 0 equal to 0. So, I get a x star equal to 0. Since a is not equal to 0, my only conclusion is x star equal to 0. Since x star equal to 0, this becomes actually the 0 0. So, there does not exist any non-zero x star such that I get the solution to be x star 0. Hence, this cannot be a solution because we already have 0 0. Similarly, you put 0 y star. So, if I put 0 y star here, this gives me 0, but from here I get minus c y star plus d into 0 into y star equal to 0. So, this vanishes, minus c y star equal to 0, which will give me y star equal to 0. So, again there does not exist any non-zero y star for which we have 0 y star as a solution, and hence this will not be the solution. And the next thing is you put x star y star where both x star and y star are non-zeros, and you will be getting this particular solution. So, there is another way of checking that how many equilibrium solutions there will be, and you get the solution. We now look into the stability of the system. So, what do you mean by the stability? So, in a very layman language, if there is an object and then you give a small push, if it comes back to its original position, we say the system is stable. If it does not come back, we say the system is unstable. Let us look in this small animation. So, you can see this plane is moving and there is turbulence. So, if the plane it comes back to its original position, then we say that the system is stable, whereas if it flips back and does not come back, then it is unstable. Let us look in the another example. As you can see, this ant, it gives a small push to this board attached and it just oscillates a little and then comes back to its original position. The same thing happens with the ball. It gives a small push, it oscillates and comes back to the original position. So, this is what we call a stable equilibrium. There is another called neutral equilibrium, that the system was already in equilibrium, it is given a small push, it moves back to a new position, but then still it is stable. Like you can see in this ball, if it gives a small push, it moves back, but in that position also it is stable. So, that is called a neutral equilibrium. And the unstable one, when the ant gives a push, so from the original position it moves back to another position, it cannot come back to its original position. The same happens with the ball, it is a push, it moves back. So, another common example is that you can consider a cone, which is an example of stable equilibrium. If you give a small push, it will come back to its original position. If I consider an inverted cone and if I give a small push, obviously it will fall down and it will not come back to its original position. So, this is an unstable equilibrium, this is a stable equilibrium. And the neutral one is, you consider the cone like this. So, if you just roll it, it will move to another position somewhere here, but it is still in the same position, but in a different place. So, this is called a neutral stability. Let us now look into the definition of stability mathematically. So, I consider the system dx dt equal to some function of x y and dy dt is equal to some function of x y. So, I assume that 0 0 is the fixed point. And let C be the path that is found by this differential equation. I also define let x equal to f t and y equal to g t be the parametric solution of this differential equation, and I define dt equal to f t square plus g t square, which means that the distance of f t and g t from the origin. Now, let us see the definition. So, it says that the critical point 0 0 is stable if for every epsilon positive there exists a delta positive such that every path C for which dt0 less than delta for some t0, dt must be less than epsilon for t greater or equal to t0. Now, this definition somewhat reminds you of the limit definition of epsilon delta. Let us look into the figure for further clarification. So, what it says is that there are two circles, one is this one dt0 less than delta, so circle of radius delta, and dt which is less than epsilon, so which is circle of radius epsilon. You start from t equal to c0, some point which lies inside the circle of radius delta, and then this is the path. So, what it says is that if your system is stable, then this path C, that must lie within this radius epsilon. So, if you can find such an epsilon and delta for which this will hold, then you say your system is stable. Let me rephrase that again. So, it says that if 0 0 is stable, then every path C which lies inside the circle K1. So, this is your circle K1, you have started for T0. So, every path C which lies inside this circle K1 of some radius, which is delta here, at time t equal to T0 will remain inside the circle of radius K2 if it is stable. If it is not stable, it may go out of the circle of radius K2. So, if you can find such delta and such epsilon for which this will hold, we say your system is stable. There is another word which you will be finding, that is asymptotically stable. Now, what does that mean and how it differs from the stability of the system? So, by asymptotically stable, it's stronger than the stability. It means that the system has to be stable, that is, all the properties that is here need to be satisfied, and along with that you must have limit t tends to plus infinity f t equal to 0 and t tends to plus infinity g t equal to 0. If you recall, this f t and g t, they are the parametric equation of the differential equation, of the solution of the differential equation. So, it means that the tiny difference that we have between the stability and the asymptotically stable, one is this mathematical, that it has to be stable, and along with that you have to satisfy these two conditions, then your system is asymptotically stable. And in stability, it means that the path which remains close to 0 0 will remain close to 0 0 when t is greater or equal to T 0. And here, along with it remains close to 0 0, the path will approach 0 0, and this mathematical condition guarantees that it will approach to 0 0. So, that is the basic difference between the stability of the system and the asymptotical stability of the system. Let us now move to the problems. So, how do you check that given a system or given a differential equation, how do you check its stability? So, we have this dynamical system of the form dx dt equal to fx. So, we will be deriving here the condition for which this system is stable. So, you have some x here and you have the equilibrium solution x star here, and the difference between them, let it be say epsilon. So, you give a small push, if it moves back towards the equilibrium position, we say it converges, and if moves back from the equilibrium solution, we say it diverges. So, in this case, your equilibrium solution x star is stable, and in this case your x star is unstable. So, you have dx dt equal to fx, and you take this epsilon, which is x minus x star. So, it is calculated from here, and this will imply d epsilon. You can also substitute basically x equal to x star plus epsilon. You are giving a small push about the equilibrium point, and from there you can calculate that epsilon is x minus x star. If I differentiate both sides, d epsilon dt equal to dx dt, and since x star is a constant, this will be equal to 0. So, now I substitute back here, dx dt is replaced by d epsilon dt, fx is replaced by f of x star plus epsilon, and I will be using the Taylor series expansion here. So, this will be equal to f x star plus epsilon f dash x star plus epsilon square by 2 factorial f double dash x star, and so on. Since we are doing the linear stability analysis, we will ignore epsilon square and higher order terms. So, d epsilon dt will be approximately equal to f x star plus epsilon f dash x star. Now, since x star is the equilibrium solution, it is going to satisfy this particular equation. So, f x star must be equal to 0, and hence this will be equal to 0, and we are left with d epsilon dt equal to epsilon f dash x star. It is a simple differential equation, and the solution will be epsilon equal to epsilon 0 e to the power f dash x star, where epsilon 0 is the initial condition. Now, if your f dash epsilon star is less than 0, then you can see that your, as t becomes large, your epsilon will move to 0, and if your epsilon moves to 0, your x will coincide with x star. So, in that case, your x star will converge and your system is stable. So, the condition that the system is stable is f dash x star must be less than 0. So, once again, if f dash x star is less than 0, then what happens? From here you can see this part is less than 0. So, as t becomes large, then your epsilon goes to 0. So, the moment epsilon goes to 0, this point and this point coincides. So, you have given a small push, but it comes back to its original position, and hence the system is stable. Whereas, if your f dash x star is greater than 0, then obviously as t becomes larger values of epsilon, and this moves away from the equilibrium solution, and you have an unstable equilibrium. If f dash x star is equal to 0, then we do not have any conclusion, we have to do further higher analysis. So, in this linear stability analysis for a single equation, the condition that the system will be stable is f dash x star is less than 0, and the system is unstable is f dash x star is greater than 0. If f dash x star is equal to 0, there is no conclusion. Now, let us take some example. So, we take the same example for which we have found the fixed point, and because you are going to find the stability of the equilibrium point or about the equilibrium point. So, if you just recall, we have the equilibrium points by taking dx dt is equal to 0, which will mean minus x cube plus 3x square minus 2x, and you put this equal to 0, and if you solve this, you will be getting x equal to 0, x equal to 1 and x equal to 2. Now, if you want to check the stability at x equal to 0 and x equal to 1 and x equal to 2, you will get, you have to take this as f(x), and you have to find what is your f dash x, which is minus 3x square plus 6x minus 2. Now, you have to consider for each x. So, for x equal to 0, we put f dash 0, or we find f dash 0, which is equal to minus 2, which is less than 0, implies the system is stable about x equal to 0. For x equal to 1, f dash 1, which is minus 3 plus 6 minus 2, which is 1 greater than 0, implies the system is unstable about x equal to 1. And in the similar manner, if you find for x equal to 2, then f dash 2. So, minus 3 into 4 plus 6 into 2 minus 2. So, which implies that the system is stable about x equal to . Now, if you want this diagram, which we will be coming later also, but for this problem you draw a line. This is your 0, this is your 1, this is your 2. So, for 0 it is stable, so your arrow will be like this. For 1 it is unstable, so your arrow is like this, that is, it is moving out of the solution. For 2 it is again stable, so your arrow will be like this. So, in this lecture we learned about the equilibrium point and about the stability of the system. In our next lecture, I will be improvising them for a system of equations, mainly two equations for the stability of the system. Till then, bye bye.